So before I jump into Math Whiteboard, I'll just give you the background story on Math Whiteboard. So Math Whiteboard has its origins in some PhD thesis work that was done at Brown University. That's where I did my PhD. That's where my team, we all did our graduate work in computer science at Brown. And we took what was a nascent research project and turned it into a tool for teaching and learning of mathematics. Let me jump in and show you what Math Whiteboard is all about. So I'm on the mathwhiteboard.com website here, and I am going to open a new whiteboard. So I clicked on new whiteboard. I'll dismiss the help screen since I'm pretty familiar with the system. I don't need those. So let me show you what Math Whiteboard is. Math Whiteboard is like a smart piece of math paper upon which I can write mathematics. So I'm writing some math, 1 + 2. Pretty simple math, but you'll see that it recognizes what I write, and I can get an answer. By the way, I should mention that I happen to be using a Windows tablet PC at the moment, and this system is Math Whiteboard is actually a web-based system, so it doesn't really matter what platform you're working on. It just runs in a browser. So Math Whiteboard can be used on a Windows machine, an iPad, an Apple MacBook, a Chromebook, and it doesn't necessarily need a touch screen. You'll see me writing a lot on the screen as I go through this demonstration, but everything I'm doing with my stylus and writing on the screen, you could do with a finger writing on a screen, or you could do with your keyboard, and I'll show you how that works in just a moment as well. So let's get back to it. 1 + 2 is 3. I've just written 1 + 2. I've gotten the answer. I can change the math, so I'm going to change the 1 to a 2. And you'll see the answer updates dynamically, or I'll change the 2 to a 3. And again, the answer updates dynamically. I can change the 3 to an A, and then I can assign a value to A. And when I change the value assigned to A from a 1 to a 2, the answer A + 2 updates dynamically. So A + 2 when A is equal to 2 is 4. I can change the 2 over here to a B, and then I can assign a value to B. So A + B when A is equal to 2 and B is equal to 1 is 3. I can change the value assigned to B to maybe a 3, and the answer, again, will update dynamically. I can write more math on the page. So A minus B, or A times B, or A over B, and get answers for all of those expressions as well. Now, there's a pretty powerful computer algebra system underneath the hood. I can do some pretty fancy things. For example, I can write calculus expressions also on the page. So here's a definite integral. We'll get an answer for that as well.
Wow.
Now, when I go back and I change the value assigned to A from a 2 to a 6, all the answers on the page update dynamically. Or if I change 3 to a 2, again, all the answers on the page update dynamically. I can even assign to A an expression like x + 1. And now x + 1 substitutes for A across the page. So learning math is about seeing connections between things. Here, we're looking at the relationship between A and B with respect to some operators, like plus, minus, divide, and so forth. In algebra-oriented topics, we look to see connections between other types of things, like algebraic expressions and graphs and tables. Let me show you an example. So here's a math expression we are all familiar with, y = mx + b. It is the slope-intercept form of a line equation. M is the slope, b is the y-intercept. I've written it on the page. It was recognized with a simple gesture, just a stroke of my pen like that, a swoop. I can get a graph. I'll do that again with a swoop from this math expression, just like that. We can get a graph. I can pinch and zoom the graph. You'll notice that we have selected default values of 1 for M and B, but I can change that. I can make M equal to a 2, and the graph will update accordingly, or I can make it equal to 3, and again, the graph updates dynamically. I can even create an interactive control for M, a slider, which allows me to show very dynamically and interactively what M, or slope, really represents. What slope? That slope. When slope is positive, it looks like this. When slope is negative, it looks like that. B is the y-intercept. When I change B, I'll create a slider for B. When I change B, we're changing something. What are we changing? Well, we're changing this point, 0, B. When I graph 0, B, we can now really see from a visual perspective what B, the y-intercept, really represents. It's that point where the red line passes through the y-axis. So there's something I say a lot. I think it's really important. Learning math is about seeing connections between things, seeing relationships. Here we're looking at the relationship between an algebraic expression and a graph. Often in the math classroom, the math teacher, the math student, the mathematician is writing math over here on a piece of paper. The primary workspace for mathematics, which is usually paper and pencil. The student, the teacher, also has secondary or complementary workspaces like a graphing calculator or a computer screen where they're looking at other representations, maybe a graph, a table, a diagram, an animation. All of a sudden you have these multiple workspaces that are pretty far from each other, not just physically, but also cognitively. What we try to do with Math Whiteboard is bring all of those representations into one workspace, the primary workspace, which is paper and pencil, and hide behind the scenes all the technical stuff. So let me show you another example that really demonstrates this in a very powerful way. I'm going to clear the screen, and I'm going to show you a related rates problem. Here are two cars. Believe it or not, those are cars.
Love it.
Not much of an artist, but those are cars. We'll say this is car A, and this is car B. And we'll give length to the road. And we'll say that car A has a constant velocity of 80 units of distance per unit time. It says the location of car A along the x-axis is defined by 80 units of distance per unit time. Car A is going 80 miles an hour. Car B is a police car that has to accelerate to catch car A. We use a quadratic to describe constant acceleration. So in Math Whiteboard, we have this ability to connect hand-drawn sketches with handwritten mathematics. It's called math sketching. So under the More menu, I can turn on math sketching. And when I turn on math sketching, we get this little slider that pops up. And you'll notice at the end of the slider, there are these player controls. You'll also notice that the math expressions on the page became color-coded, and the expressions match up with the labels on the cars. So when I press the play button on the slider down here, the timer control, we see the cars moving across the screen in an animated simulation as described by the math.
Love it.
Pretty cool. Pretty cool for us as adults, as teachers. Imagine what happens when you show this to kids in the classroom, right? Their heads explode. Make the car go faster, make it bump up and down. All of a sudden they're engaged and they're asking really great math questions that require knowing more math in order to answer the question. So for example, how do you make the car go faster? How do you make it bump up and down? But more important than that, what we're doing here is we're connecting this abstract mathematical notation that you see on the left here with a very concrete example. So the students can see how the math matters. Why does the math matter? An experience from the real world, cars driving along the road, can be associated with this abstract mathematics notation. And of course, this is a related rates problem, and related rates problems are very common across mathematics. In algebra, for example, here we would be looking to answer two types of questions. The first question, or two specific questions typically you'd see on the exam or a standardized exam. At what point in time does something happen, and at what point in distance does something happen? The point here that we're looking for is when does the accelerating car, car B, overtake the speeding car? We can see it happens right there. Well, that's an observation, not a math answer. We want to get the math answer. How do we get the math answer? Well, there's a couple of different ways to get to the math answer here. As you learned earlier, we have a powerful computer algebra system underneath the hood here. And if you're advanced enough in your knowledge of mathematics and the way related rates problems work, you might know that you can set the equations equal to each other and then solve for t. So for example, we could set a sub x equal to b sub x and solve for t here, and that will give us the intersection points between the parabola, the quadratic, and the linear. But oftentimes you don't know that you can do that because you're just learning about systems of equations. So another approach to solving this problem is to use something like the scientific method, where you come up with a hypothesis, you test the hypothesis, and then you prove it. So let's do that. Let's come up with a hypothesis. The way we can do that in algebra is we can graph functions, and we can look at the graph of the functions. I can pinch and zoom this. We can see that something interesting is happening in the graph. There are points of intersection. There's a point of intersection at the origin, and then there's one out here in the quadrant. The point of intersection at the origin, that's where the cars start. and the point of intersection out here in the quadrant at time equals 8 and distance equals to about 650. Well, that's the point at which the quadratic, obviously, the parabola, overtakes the linear. And our hypothesis will be, well, that's when the accelerating car overtakes the speeding car. So let's test the hypothesis by running the simulation again. So I'm going to turn on the math sketching one more time, and I will move the slider bar, the timer, over to 8, because our hypothesis is when time equals 8, the car should be at the same spot. Move the timer to 8, and we can see that, well, it looks like the cars are at about the same spot. So we know that the hypothesis is approximately correct. It could be 7.9 seconds or 8.01 seconds, but we know we're on the right track. Let's prove it. The way we prove things in algebra is through substitution. So I can substitute into our functions here the value of our hypothesis when time equals 8 and solve for a sub x. If a sub x is about 650, we can see from the graph, which I want that to be an arrow, we can see, oh, it's 640. That's pretty close to our hypothesis. If b sub x is also 640, we have proven the hypothesis. Okay, cool. We just proved the hypothesis. That's great. What I love about this example is it shows the power of having multiple representations in one workspace, and everything's connected. So, we've got algebraic expressions, we've got a graph, we could look at a table of values, we've got a simulation, we've got a solution, and everything is connected. So when the student says, hey, make the car go faster, well, we can change the speed from 80 miles an hour to 90 miles an hour. And I just want to move that over here. And we can see, oh, all of a sudden, the graph changed. The point of intersection moved to over here, and the solutions changed. If I ran the simulation again, we would see that the accelerating car wouldn't quite catch up. So let me pause for a moment, see if you have any questions.
Yeah.
There's several other things I'd like to show you.
I think the biggest thing, Don, is how easily and fluidly you were able to bring up, like you showed us the table, right? Sorry, the graph with the little swoosh shortcut. But you also brought up that table. That was just with the click of that button, right? It says table there on the graph, and you can just pop out that table. Is that correct?
Yep. Right there on the graph. So when I click the table, it's a toggle. When I click it, the table goes away. If I click it again, the table comes back.
And then the other part was to bring up this ability to be able to do this animated feature that was under where, Don? Up
Yep.
there where it says more?
Under the More menu, the first menu item is animation/math sketching. You turn that on, and it associates your handwritten mathematics with hand-drawn sketches. And we use a particular notation here to do that. It's a pretty common notation you'd see in math, I think, where anything with a subscript of X or Y, when math sketching is turned on, would be associated with a label for an object. And the label for the object in this case is, so for example, the label A is associated with the closest drawn object. Yeah, there's a couple of I think you're raising a really good point. Just from an introductory perspective, I have been switching back and forth between several modes here. There's a drawing mode that allows me to annotate on the page. There's a math writing mode that allows me to write mathematics on the page. So when I turn on math and I write 1 + 2, you can see that it is recognized. If I were to use the draw pen and write 1 + 2, it's not recognized. It's just an annotation. I can also write a smiley face, and it's not recognized. But if I were to write a smiley face with my math pen, well, the recognizer will have a tough time with that because it doesn't really know what I'm trying to write there.
It's not sure what you're trying to do.
It seems to think that I'm writing 0 to 0 degrees or something like that. So obviously not correct. There's a couple of other things just from an introductory perspective here. I've been using several, we call this a gestural based user interface. So for example, I've used several gestures. If I've written some things, so 1 + 2, and there's a scribble erase gesture, which you've seen me use. Just scribble out something and it disappears. If I were to write, y equals 2x + 3, and whoops, I want that to be a plus. And let's say I want to change the 2 to a 3 here, or let's change the 2 to a 6. So I can just scribble this out, this 2, and I can change it to a 6, and the math updates accordingly. So that's the scribble erase gesture. There's also a graphing gesture, which you saw me do, which is the swoop gesture. So from a math expression like this, we just swoop and we can create a graph like that. If I had changed this to an M, we had a slider. And the way we create a slider is we write an assignment, like M equals 1 in this case, and the straight line down from the equal sign creates a slider. I'll do that again. So M equals 2. And then a straight line down from the equal sign of an assignment, just like that, creates a slider.
Nice.
So far, those are 3 gestures: the scribble erase gesture, the graphing gesture, and the slider gesture. There are 2 more gestures that are possibly useful, but I think less frequently used. There's a gesture to create a 2D coordinate plane. That's a big plus, like that. Creates a 2D coordinate plane. Just an empty graph upon which I could graph if I wanted to by just graphing into the graph area. And there's also if a big plus is a 2D coordinate plane, a straight line is a number line, a 1D coordinate plane. So now I can graph things on that, like x is greater than 3, maybe. And I can graph that with the swooping gesture. I can also be more dynamic if I want to do x minus h, and then assign a value to h, and then maybe create a slider for this. And now we can show the value
Awesome.
on the number line. So those are the basic gestures, basically 5 basic gestures you can use. It's a small vocabulary of gestures to really, control the workspace.
Don, do you imagine, as far as on the teaching side, how you would use this would be in those situations where you have some direct instruction, and you're trying to maybe give examples for the students, right? Or what are some ways that you have used it or envision other people using this? Like as far as what part of the teaching and learning process? 'Cause I'm sure there's several different points.
That's a great question. I think of it being used in a couple different ways. The first way in which this is used or can be used is as a presentation tool. It provides a mechanism for really quick presentations of concepts. There's no moving off of the workspace to a different workspace to present a graph or present a table. You're always staying within the same workspace, and it's very fluid. You're using your natural handwritten mathematics notation to present. So it's, again, it's like a smart piece of math paper that can be used for presentations. And, the idea here is that we wanted users to be able to move very fluidly between representations, and that's what the gestures really enable. The other mechanism, or the other way in which this can be used in teaching and learning for the teacher and or the student, is that this is actually a collaborative workspace. So it's not just me using this alone. I can share this workspace with others. So it could be me as a teacher sharing this with 1 or more students. It could also be multiple students working together collaboratively to solve problems. So let me show you how that works.
Yeah.
I'm going to bring up a separate browser window here. So I've got 2 browser windows. The browser window on the right here in this first example will be maybe the teacher, and the browser window on the left will be used by the student. And of course, these 2 browser windows represent users on 2 different computers, and these users don't have to necessarily be in the same room. They could be, each individual could be at their respective homes. The teacher could be in the classroom, the student could be at home. And also, this could also be, because of social distancing requirements these days, we may want, the student and the teacher to be sharing a workspace, but not, sitting on top of each other or using the same piece of paper or the same whiteboard. Instead, this enables the sharing of a collaborative space in real time via, the computer and technology. So I've got this whiteboard on the right-hand side. You'll notice at the top, there's a there's a link listed. Actually, the browser, in the browser window, you'll notice a link, and that link is unique for every Math Whiteboard that's created. It's also copied here into your browser window. And if I click the copy link button, that will give me a copy of this URL placed in my clipboard that I can do anything with now because it's in the clipboard. I can paste it into a Google Doc or a Google Classroom or my learning management system or an email to my student. And when the student clicks it, of course, it shows up in the browser. I'm going to paste that right into my browser window here. And now all of a sudden, these two users are sharing the same collaborative math workspace. So for example, I'm going to write something on the right-hand side here, y equals x. And you'll notice as I write it on the right, it is displayed on the left. It's not only displayed on the left, it's alive on the left. So the user on the left, maybe the student in this case, can edit it. So for example, the teacher might say, well, change that standard form into slope-intercept form. And the student can edit this. And now, so I had just edited that on the left-hand side. So initially I wrote the y equals x on the right-hand side. I just changed it on the left-hand side. And all of the tools that you have available in Math Whiteboard are here. So I can create sliders. And I happen to be alternating between sides here of the browser, between browsers.
Yes.
You can't see me doing that. It's difficult to demonstrate the real-time collaboration because you see them both in real time happening. But I happen to be alternating my pen from one browser to the other browser.
You can see the delay as you write on one. It just then it appears on the other one, so it is working. Yeah, I can see that.
Yep. And just, yeah, there's just a slight delay. The ink is really very close to real time. So that's you were asking about the modes in which this might be used by a teacher. This would be the second mode in which it's used, where a teacher would be working with one or more students. And the idea here is that the value of a real-time collaborative whiteboard in the math classroom and in math instruction is that it provides a synchronous mechanism for the communication of mathematics. So for math teachers who have been in the classroom for 5 years, 10 years, 20, 30, 40 years, faced with, well, they're in the classroom for that period of time, doing synchronous communication with their students. That's the classroom environment. It's real-time synchronous communication with your students because they're in front of you, they're in the classroom. But now we're faced with these distance learning environments where you're no longer in the classroom in real time with the students. Or maybe you are, but the communication of mathematics is really challenging because when you're communicating mathematics, it's important to be able to see it and hear it at the same time. So when I'm writing math, I'm also explaining it at the same time. Sometimes you can do that asynchronously, but oftentimes for some learning experiences, having the synchronous communication, both visual and through speaking, is really important. So let me, yeah, any other, there's a few more things I'd like to show you, but any questions in addition?
No,
there?
I think this is fantastic. Great examples. There's that collaborative piece. There's the direct instruction type of piece. Obviously, creating even, I was thinking about flipped instruction, using this powerful tool as basically your drawing board. You can do that also. And I know a lot of teachers are using, whether it be dot cameras, on a piece of paper, like you said, to be able to record some of these things, or some other kind of software like Notability to be able to just write on. This gives you that kind of next level tools to be able to go ahead and show multiple things very quickly as you're working through them.
Absolutely, yeah, that's the key. The key, one of the things that I think we have learned over the years in our research, I think I mentioned earlier where we come from a research background. So one of the things we do is we really study this from not only a technical perspective, but also from a pedagogical perspective. And one of the things that we've learned is that being able to show a lot of examples is really important for a learning experience in mathematics. So that's one of the things that Math Whiteboard enables. It's showing examples, a lot of examples, really quickly. So let me continue on with a couple of other bits of functionality that I think you might find interesting. I'm going to dismiss the window on the left here for the moment. I'm going to expand the window on the right, I'm sorry. And I'm going to just start up a new whiteboard. As I mentioned earlier, there's a keyboard-based interface. So for your students or teachers who might have devices where they don't have a touch screen, or maybe they just don't like writing on the screen, they prefer typing, we have this keyboard-based interface. And as I mentioned earlier, you can enable the keyboard-based interface for mathematics up here by clicking on the math typing button. So I click on that. And now I can click on any location within the workspace, and I can type math. You'll notice when I clicked on the space at that location that a virtual keyboard on the bottom showed up. I can use my physical keyboard. I'll start with my physical keyboard. So I'm just going to type y equals ax squared plus bx plus c. That's me just using the physical keyboard. I can also, if I prefer, use the pick and peck virtual keyboard down at the bottom here. I can type y equals x squared. And I can click and drag these expressions around if I want to. If I wanted, here's a little trick. If I wanted to put a graph on the page right now, oftentimes new users will think that they can use the swoop gesture. So they think, well, maybe I can just swoop this thing and it will create a graph. That's not the case. What you really want to do is put a blank graph in the graph area. I could do that in a couple of different ways. As you learned a couple of minutes ago, we can draw just a big plus, and that will give us an empty graph into which I can drag these expressions. I can also put an empty graph onto the workspace with the insert menu. So I can go to insert and click on graph, and we can get a graph on the page. Or the next one is down here. There's an add graph button down here on the virtual keyboard where I can click add graph. And all those mechanisms put a blank graph area here on the page. I can drag and drop these into the graph area. And if I click on, in these math expressions, these typed math expressions, if I click on A, click on B, and I click on C, I get these dynamic control sliders that allow me to show the transformations of this function.
I love it.
And by the way, if I wanted to, I could put another blank graph on the page here, and drag and drop other math expressions into the graph area. So you can have multiple graphs in the graph area at one time. So that's the keyboard-based interface. So again, for your users who might not have touchscreen devices, maybe they have MacBooks or Chromebooks without a touchscreen, it's everything I've done so far and everything I'm going to show you or have shown you that I've used my stylus for writing on the screen, you can do just as effectively with a keyboard and a mouse.
It's fantastic.
Oh, thanks, Glenn. Let me show you a few more things here. One very practical thing that you can do with Math Whiteboard is leverage or utilize some of the resources that you already have. And many of the resources that mathematics teachers have come in the form of PDF files. So your typical math teacher might have hundreds of PDF files neatly organized into categories. I have about 9 here, but here's an example of a PDF file, solving systems of equations. I'm just going to open that one up and we'll take a look at this worksheet. It looks like any other worksheet. It's a PDF file with some questions on it that look like math questions. But I can take that PDF file and drag and drop it right into my Math Whiteboard space. And it now becomes, that PDF file becomes the background for my Math Whiteboard page, upon which I can do all of my cool Math Whiteboard stuff, like write math expressions or get solutions. Maybe I want to say 1 + 2 here and get a solution, or I can graph this function over here. I can annotate here and step through these solutions to the problems. So all of a sudden, what was a static PDF file becomes a live, dynamic, interactive PDF file that we can share digitally.
Super easy too. I love the drag and drop just right into the thing. Yes.
Oh, yeah. Oh, totally. So a couple more tidbits here that I think are pretty cool. There's a bit of really neat functionality here that I don't think you'll see anywhere else. It's we have this ability to test for equivalences and equivalent expressions on a page. And let me show you what I mean by that. So under the More menu, if I turn on Highlight Equivalents, all of a sudden, anything anything I write or type on the page will be color code matched with anything else that's equivalent. So for example, the number 3 and the number 2 are not equivalent. You'll see that they're color coded differently. And the number 4 is not equivalent to the number 2. So again, it's color coded differently. But the number 6/3 is equivalent to 2. So it's color coded the same as 2. And the number 4/2 is equivalent to 2. So it is also color coded the same as 2. Pretty cool for numbers, but also really cool for algebraic expressions. So here are a few identities. A plus B and B plus A are equivalent. So they're color coded the same. But A minus B and B minus A are not equivalent. So they're color coded differently. And A times B and B times A are equivalent. So they're color coded the same. But A over B and B over A are not equivalent to each other, so they're color coded differently. This is great for simple algebraic identities, but it also extends to more complex identities that you might find at higher grade levels like Algebra 2, pre-calculus, and calculus. An example of that would be a trigonometric identity. So for example, we know that tangent of theta is not equivalent to sine of theta. So I want that to be an n. Not equivalent to sine of theta, so they're color coded differently. But sine of theta over cosine of theta is equivalent to, whoops, I have an extra dot in here. Get rid of that. So now these two expressions, this is a trigonometric identity. Those are equivalent to each other. This is great for identities, but it also is potentially really powerful for step-by-step problems. So for example, here's a simple algebraic expression: 2x plus 3y equals 4. Right? If we wanted to, excuse me, if we wanted to solve for x here, well, the first thing we might do is we might move the 3y over to the other side. So we want to move plus 3y over to the other side. How do we do that? Well, we might say, 2x equals 4, and this is plus 3y moved over, so we're going to say plus 3y. You'll notice that the second expression is not color-coded the same as the first expression, and as we know with step-by-step problems, each step should be algebraically equivalent to the previous step. So we must have done something wrong. What did we do wrong? Well, obviously, we forgot to change the sign when we moved the plus 3y over. That should be a minus. And now we can see that the first step and the second step are color-coded the same. Therefore, they're equivalent expressions. I've received a visual cue indicating that, oh man, I made a mistake. Now I fixed the mistake and I can continue on with the solution. And the next step in the solution would be x equals 4 minus 3y over 2. So pretty powerful, not only for the learner who is receiving these visual cues, but possibly also the teacher, because we're all human, we make mistakes, and this is just a couple of steps here. For many algebraic problems, there are many more steps than just a couple. So sometimes as adults we make mistakes. We're all human. If we were to make a mistake early on, and then we get to the bottom and we say, oh darn it, we made a mistake so early on, I have to go back and redo everything, potentially very helpful in that circumstance as well.
Yeah, I think super powerful there. That would have been very helpful in my Algebra 2 class.
Oh yeah. Yeah, totally.
For me, myself.
It's important to get, sometimes it's very important to get like that immediate feedback, because that's when the learning happens. Yes. If the feedback is too delayed, then, as a learner, as a young learner, sometimes you're not focused as much on understanding what the mistake was, instead of the circumstance where you can try to understand it as you're working on it and as you're seeing the mistake happen.
And a lot of times we get formative feedback, Don, as far as specifically for math or anything else, and it has the answer on it, yes, but not the process, not as you're actually working through it. So that's why I really love this. You were working multiple things there, and it was telling you whether or not you were on the right track or something is awry here. So yes. I love that.
Yes. And by the way, this works with the keyboard as well. So if I were to, I'll just turn on the keyboard math here. If I were to put in, x squared, and then I enter, 2x is not equivalent to x squared, so it's color coded differently, but x times x is equivalent to x squared, so now it's color coded the same. So, so the keyboard color coding of equivalences works just as effectively as it does with handwritten math color coding.
We do have some upper level math instruction. I think you showed me some things that related to trigonometry, I believe, and then also maybe even some pre-calc or something like that. Can you do a quick demo of any of those?
Yeah, sure.
Okay.
So I would say the application of Math Whiteboard is most commonly used within pre-algebra, algebra 1, algebra 2, pre-calculus, and some of calculus. Let me show you an example of something that you would see in possibly algebra 2 or in pre-calculus. This is a transformation of a trig function. I think this is really powerful because it really demonstrates the connection between something visual, that concrete that you would see, as well as abstract. So this is a transformation of a trig function example. So we'll take a look at y equals a times sine of bx plus c plus d. This is a standard form of the trig function here for sine. I can graph that. What I'm going to do is I'm going to turn off highlight equivalence for this example because it's not really applicable. Now, one of the things that we teach when looking at transformations of trig functions is that each of these parameters are like knobs. And there's a vocabulary word associated with each one of those parameters, and I'll tell you what those vocabulary words are. Actually, I can just leave these arrows here. I'll tell you what those vocabulary words are in a moment, but let's take a look at the knobs to start with. So A, and by knobs, I mean, we're going to create controls, sliders, to just demonstrate what each of these parameters really does in terms of the transformation of the function. So I'll create sliders for these. And now when I change the value or the slider for A, we can see that the graph changes. And just visually, we can see that the graph is squishing in the vertical direction and stretching in the vertical direction. That's called amplitude. That's the vocabulary word for A, amplitude. For B, we can see that the graph squishes and stretches in the horizontal direction. There's a vocabulary word called period or frequency, which applies for that. The C is a parameter that causes the whole graph to move left and right. That's called horizontal translation or horizontal shift. And the D parameter that I'm changing now, we can see that that causes the whole graph to move up and down. That's called vertical shift or vertical translation. So, it's really powerful to be able to see the multiple representations in one workspace and see everything connected. And to be able to do it really quickly and fluidly. That's one of the things we enable with Math Whiteboard.
Yeah, when I saw this example, this was the one where I understood things that I hadn't previously understood. So that made it really clear as far as the connection between all of the visual cues and then, like you just said, the knobs. So very, very powerful there.
Yeah, I think it's important to be able to see the math, be able to touch the math and see it change to really get a feel for it. Because once you've appreciated what these knobs are doing, you can all of a sudden apply that in other ways. So for the best example I can think of here is, or the simplest example, is this D parameter over here. I'm gonna get rid of these here. So this D parameter here, that's there's a really simple thing happening here. Whenever you have a y equals on the left-hand side, and then you have some math expression followed by plus something, in this case plus d, that d is going to, whenever you change the d, the whole graph is going to move up and down. So for example, if I had y equals mx plus d, and I graph that, and then I change the d parameter, well, we can see the d parameter having the same effect on both of those. If I did another graph like y equals x squared plus d, and we graph that, now again, that d parameter causes the same thing to happen. So there's this kind of universal principle that the thing hanging off the right-hand side of that expression there, it doesn't really matter what's happening here. It's the d parameter. When I change that d parameter, it doesn't matter what sort of the core expression is there. The d parameter causes the same thing to happen across all math expressions of this similar form. I think that's really powerful. And the ability to show this type of thing so quickly is really what makes Math Whiteboard really powerful.
So fantastic. Anything else, Don, that we should go ahead and know as far as Math Whiteboard, or when our teachers are working with it or experimenting with it?
And let me show you just a couple more things here. So I'm going to create a new math. I just click new Math Whiteboard. We get a blank slate. We have a text box mechanism that allows us to type math on the page. So I can type math there, but typically you're typing math to, or you're typing text on the page to explain something. So let's take a look at a math expression, y equals mx plus b here. And I'm going to graph this, and then I'll take a look at m as a slider and b as a slider. Whoops, did that too fast. Oh, by the way, let me get rid of these sliders. Underneath the handwritten math, that's actually a button. When I click the button, my handwriting goes away.
Oh,
and
yeah.
now those free variables, m and b, are clickable. I can click on those. And now I've got sliders for m and b. So that's sometimes a
little faster then too. Yeah.
A little faster, but also what it does is it puts a more well-formatted presentation on the page. So my ugly handwriting doesn't have to be on the page taking up so much space. Instead, I've got this more well-formatted math, which looks nicer. Now, if we go back to the text box and we type in some instructions, so for example, I might type in play with the sliders to understand the transformations, something like that. So that's a text box with instruction, right? But oftentimes you may want to put another representation on the page. I have queued up here a YouTube video. We can, with these text boxes, embed a YouTube video on the page. So I'm going to put a text box over here on the page. I'll edit it under the insert menu. I click on media, and now I can enter an embed code. I have a SolCon video queued up here in my other tab, and we all know that with YouTube videos, we can, I'm just going to click pause. We can click on the share link here, and we can get embed codes. So I can click on embed, and then I can click on copy here, and that will copy the embed code to my clipboard. I go back to my Math Whiteboard tab. I'll paste that embed code in here, click save, click OK, and now all of a sudden we have got a YouTube video embedded in our Math Whiteboard page, and it's live. It's not like I click on this and it opens up YouTube. I click on it, and all of a sudden it's playing the YouTube video right in my Math Whiteboard space. So again, another representation that's presented in the Math Whiteboard space, and everything is in one primary workspace. I'm not switching back and forth between tabs or devices and so forth. So one last thing, and this is a very practical item as well. Math teachers oftentimes will, or math administrators, will design exams, assessments, and so forth. And mathematics notation happens to be something that's a little bit challenging sometimes to enter into, like Microsoft Word or a word processor. We make that a little bit easier for you. I'm going to write just a math expression on the page here that might be a bit challenging to enter with your keyboard, or to use the mechanism within a word processor to like the virtual keyboard that they give you, which isn't always all that powerful. So for example, here's a math expression that might be might be a little challenging to enter with your keyboard. I'm just going to make something up here. So, we've got a fraction, we've got an exponent, we've got a couple different layers here. If I right click on this math expression, I'm just going to right click on this. I've got something that pops up here. I can copy various typesetting formats into my clipboard. The one that works best for Microsoft Word or for some other word processors is the presentation MathML. So I click on copy presentation MathML, and now I've got that math expression copied to my clipboard. I'm going to pop up Microsoft Word here and hit Control V, and all of a sudden that math expression is now in my Microsoft Word document. So I don't have to spend all that time using the equation editor in the word processor, which sometimes is a little clunky, and instead I can hand write my expressions or type my expressions with the math keyboard in Math Whiteboard and just paste them into my assessment or my assignment that I'm creating in Microsoft Word.
Very, very easy. Very practical. Love it.
Awesome. So I think I covered, it does a bit more, but I think I covered enough to whet the appetite of any math teacher out there that would like to learn about what Math Whiteboard is capable of.
Yeah, Don. If our math teachers want to get in contact with you, we just go ahead and reach out to you by email, right? And then you're also have a Math Whiteboard account on Twitter, I believe, that I'm following right now. And is that the best way to get a hold of you?
That's correct. Yep. You can email me at donald.carney@mathwhiteboard.com. You can feel free to forward my email address if you'd like to. And yes, Twitter is a great place as well.
Perfect. Thanks so much, Don. Really appreciate it. Thank you so much for letting us record this. And we'll reach out with questions. And I mean, this product is amazing. Thank you for creating it and then for sharing it with us.
Oh, thanks, Glenn.